Australian audience need introduction because Saifur is like a celebrity here, at least in my city of Perth. Saifur was drawing the biggest crowd historically to his talks. So very well known in Western Australia and I think in the rest of Australia. But just quickly, before I start this introduction, I should make everybody aware that this event is being recorded. So I'm not going to read the bio, so everybody has it, so they know. But Saifur Rahman is the founding director of Advanced Research Institute at Virginia Tech. So he was the Power and Energy Society president for 2018 and 2019. And he has a lot of legacy through this presidency. So the 2 years that Saifur was the president of Power and Energy Society, there were a lot of initiatives that have been put forward and continuing as a result of this presidency. So he initiated the China Council, he initiated the India Council, he did a lot of good works in many fronts. But for Power and Energy Society, he was the editor-in-chief of the also IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. He has many, many papers and journal papers, and he is having a lot of positions in different sort of capacities. A distinguished lecturer of IEEE, and his contribution to smart grid, energy efficiency, energy internet, blockchain, Internet of Things has been well received, and he's been having those talks and contributions in many, many countries around the world. The purpose and the subject of this presentation is the role of a smart grid in facilitating renewable energy, and I make it short and I'll leave you to Saifur Rahman. Thank you, Saifur, for accepting to talk to us in Australia.
Good evening, Dean Sharafi and all my friends. I see about 100 names already signing up. Very pleased to see this strong turnout. As you look at the title for my talk, the two items here, smart grid and renewables. Both of those apply very well in Australia. Dean mentioned my speech or keynote speech in Australia many years ago, distinguished lecture program. I remember the meeting was supposed to be held at the power company auditorium, but top topic was smart grid. It was 2010, I think, that time frame. It was new at the time. So many people signed up. They had to move the venue to the Science Museum so they can host more people to listen to this talk. That's, I felt really good that common people are interested to talk about smart grid. So that's how I started with smart grid. This is a long, long story. So let me move on then. Again, I am going to give the talk for about 35 minutes or so, leaving plenty of time for questions, and you can ask questions on the chat box as well. Okay, let's move on then. I will, first of all, look at the definition of smart grid. We as engineers, we hear something new, we tell the presenter, define for me what you mean by this. Smart grid is not one complete thing. To me, and to many people, it's a concept where many elements come together, dealing with the monitor and control, generation, transmission, distribution, and smart, and end use, keeping in mind, not just monitoring, control also. Your smart meter in the house can control your voltage, for example. That's the important thing. So we focus on the generation, transmission, distribution, end use, and both supply and delivery of electricity. That's where I am coming from. So when we talk about a grid means a network. In our case, the electric power grid, which is a power network, is already quite smart. It is filled with high technology, PMU, facts, and many other things. Many of the people in the audience I see here have done work in power systems. You know as well as I do. That's quite smart. So if that's the case, where is the problem? Well, before I say and talk about the problem, let's ask the question, why do we need the smart grid to begin with? What is the motivation? Well, here it is. We want to make the grid smarter, safer, reliable, and more cost-effective. Keep in mind, cost-effective, using advanced sensors, communication technologies, and distributed computing. Going backwards, why do you need distributed computing? If you have so many devices all over the place, you cannot collect all the data and bring them to the control center. There's too much information. So we try to do local computing, local action. For example, you can have a smart transformer, which would change the voltage profile of the individual homes to control the power flow, for example. Cost effective. I didn't say it is cheap. Smart grid is very expensive, but it is useful. The way I explain things is the following. To me, this is the way I tell common people what is a smart grid. People know about a phone, normal phone, and a smartphone. Normal phone, the black one on the left, has been around for, 70, 80 years. In the US, costs about $10, $12 a piece. Fine, it works. You can pick up the phone, talk. Phone means phone, talk, right? Works. Then you have a smartphone. If you buy a, iPhone version 11, costs you about 1,500 Australian dollars. So why should you spend that much money, 100 times more than a black phone on the left, just to talk? We still buy smartphone. Why? Because smartphone gives you not just phone, gives you Instagram, Facebook, email, camera, timer, watch. You name it, music, video, they talk about YouTube, all of that. That's why we are willing and able to spend that much money. The point is the following. If you are convinced that some new technology will give you more than what you're used to, you will spend the money. That's how I talk about a normal phone and a smartphone, normal grid and a smart grid. So let's move on to go into more depth. What then are the building blocks of the smart grid? Or let's first talk about starting point and ending point. Of course, we know how the system works. Power plant, transmission line, distribution network, office building, homes, and then your end user appliance. All of that from beginning to the end, to me, is the smart grid. So I say the smart grid starts at the generator, ends at the refrigerator. Somebody might ask the question, does that mean the power company can see when my refrigerator turns on, how many times I open the door, when the light comes on? In theory, yes. In practice, no. Because the regulations don't allow power company to scan your demand every few seconds to see what's going on. If I'm allowed to scan your household meter every 5 seconds, I can tell you when you turn on your hairdryer, when you start the toaster, when your fridge compressor goes on in effect. I can say that. But in our case in Virginia, when my house has smart meter, for example, the power company monitors the load every 15 minutes, not every 15 seconds. From 15 minutes, a lot of things get averaged out. They cannot tell when I turn the hairdryer on or my toaster on or my fridge comes on. Issue is, yes, in theory it can be all the way down to your end-use device, but regulations don't allow that. That's why we feel safe. So that's the starting and ending points of the smart grid. Next is, what are the building blocks of the smart grid? At the top is the technology of this pyramid. That means we have to have technology to make the grid smarter. Like talk about PMU, talk about smart meter, talk about digital substation, talk about switchgear, automated switchgear, and the like. Those things already exist today, and they are being improved upon. That's not a challenge anymore. It's there. Next question is standards. As you know, smart meters are made by many companies worldwide. So if you have a utility like Western Australia, they want to deploy smart meters. They cannot afford to depend on only one company, one supplier, because of cost, reliability, and many other things. So they can buy from multiple vendors. For that to happen, all the vendors which are supplying electricity to the power company must follow some standards. And those standards today exist. They're not a problem anymore. It used to issue 5-6 years ago, but now standards exist and globally accepted. Then the issue is rates and regulations. Why do you use smart grid or smart meter? Let's begin with smart meter first. We in some parts of the US have what you call variable rates based on demand or based on time of day. If the rate of electricity is high to the consumer, let's say between 1 p.m. and 6 p.m. on a hot summer afternoon, because the consumer is using air conditioning and many other things, power company is hurting because everybody is demanding more and more power. They have to produce more electricity, and they have to go to expensive generation, gas, oil, whatever it is. The rates say if you, the customer, can regulate or use less electricity during high peak periods, you'll get some incentives, some discount, some electric bill credit. Those rates and regulations are not very universal yet. Unless that happens, the full benefit of smart grid will not be realized because there's no incentive to do this. So this is happening. At the bottom of the pyramid, the blue box is consumer awareness and education. You and me are engineers. Most of our engineers, power engineers, we can figure this out quickly. Talked about my neighbor who is a, banker, and he doesn't know what these things are. So he doesn't know or doesn't appreciate the need for changing or reducing his demand at 4 p.m. on a summer afternoon. This is the challenge in the US and many countries globally. We have to make sure that the consumers, the end users are aware of, at a high level, the benefits of a smart grid. So, and only then they will be willing to invest their money, meaning to electric bill, to deploy smart grid. Example, in Virginia, on the average, it costs the power company $250 US to deploy a smart meter. Not the meter cost. Meter costs $60, $50, $60. Cost is infrastructure, a network, communication, computers, manpower to manage it. That's expensive. That $250 is the cost. It is in the long run paid by you and me, the customers, because part of our electric bill. So why should I pay that unless I see the benefit of it? So this is the challenge, and make sure we understand this so that the cost can be properly justified. Okay, now, how has the grid evolved over the last 10 years, let's say? The top third of this picture, before smart grid, we have one-way power flow. That's standard for more than 100 years now. Starts at the power station, produce electricity, step-up transformer, goes to the transmission line, the power travels long distances, comes to your neighborhood, step-down transformer, goes to the distribution line, and finally to your home or office. This is how it is, no problem. If you go to smart grid, why is that important? New things are showing up. The rooftop solar. Australia has quite a few. In Perth, I've seen many homes have rooftop solar, in fact. Storage battery. You have electric vehicle. You have wind turbines. You have local control. All of that is happening. So how to manage all those things? You must know who is producing how much power when, and is somebody willing and ready to sell power back to the grid. So those issues have to be dealt with. That is why we are putting, you notice in this picture, dotted blue lines. Those are communication lines so that information can flow back from the end user to the control center. In Virginia, where I have smart meter, how does the smart meter data get transferred to the control center for my electric power company here? First of all, the smart meter transmits information using mesh network microwave. 100 or so buildings, meters, transmit data to what is called data concentrator using this microwave mesh network, which was put in place by the power company. It goes to the concentrator, which transmits the combined data from this neighborhood to the substation using GPRS, your mobile phone network. That network is rented by the power company to transfer data. Since they're measuring every 15 minutes, the volume is not that high. The cost is not very high for the power company to use the commercial cell phone network, mobile phone network. Once it goes to the substation, from there, power company itself has fiber optic network to the control center. That is then using their network to get data to the control center. So that means all that has to happen in real time. That's the challenge we have to work on. Okay, so the way I look at smart grid from the conceptual viewpoint, to me, smart grid is a collection of many microgrids. What's a microgrid? In this picture, I have 4 microgrids. On the middle, top middle, I have 4 homes, rooftop solar, and a data communication network. So figuring out what's going on at every house. I also talk about transactive energy. That means a home, if they have excess electricity, can always sell power back to the grid. That's allowed. But in this case, inside a microgrid, a home can sell power to a neighbor directly, not to the power company, and transact business based on cost and benefit issues. So I can make more money if my neighbor is not able to meet their load using their capacity. I can sell my excess PV to them. So a lot of things are happening as we go forward. So that's one example. In the middle of this picture, I have a bigger microgrid. Still, that bigger microgrid is connected to neighboring microgrids, so it is a bigger footprint. So those things are happening at the edge of this picture. On the upper left, you have a power station. On the lower right, you have the bulk power plant. On the lower left, you have the wind turbines. All of that is part of the network, what I call interconnected microgrids. Okay, moving on down. So this is the summary how we design the system. We are saying here, we have to merge power flow with information flow. That means we have to integrate communication network, like you saw in the previous picture, with the power network. So this is how, let's go back. This is how the power network is set up. If you look at this picture, on the upper side as the number 1 power infrastructure, then you have the black, follow the black lines first, which is the power station, transmission line, receiving station, receiving substation, local gas turbines, network, distribution system, all that. This is there. I have done something on top of this. If you now look at the red lines with the arrows up and down and left and right, I call that information infrastructure, meaning I am now overlaying the electric power infrastructure with telecom network. As I said before, how does the information go from my house to the control center? That's information infrastructure. Mesh network, mesh microwave data, GPRS, and then fiber optic line. That's information infrastructure. That is new. That was not there 10 years ago. Okay, now, why is that important? The situation is changing, I say changing landscape in the electric utility industry. We get wind, offshore, onshore wind. On the right side, on the top side, I have the rooftop solar. That's in Japan. I could have shown you a house in Perth with similar rooftop picture. Maybe I should have shown that. Maybe Maybe Dean has a solar rooftop on his house. I know my friend Said Islam, when he was in Perth, he had rooftop solar. So anyway, this is possible. Then you got electric vehicle, which is coming in large number. This is Tesla car, which has a 60 kilowatt battery. You hook this car up in your garage, you'll be pulling 30 kilowatts, 30 kilowatts. The whole house doesn't pull that much power. So what do you do with it? You got to make sure this can be handled. Otherwise, they would not sell electric cars. This is the changing landscape that we need smart grid to work with. Okay, now what are then issues with distributed generation? As you know, we have solar, we have wind, we have hydro. Especially wind and solar are intermittent. There's no guarantee that you'll have solar tomorrow morning. It may or may not happen. Hydro is not that problematic, but hydro is space limited. Yes, I have been Perth many times. You can walk by the water side. We cannot put a hydro plant there because you cannot dam the river and flood the rest of the city. That's why I'm saying hydro is space limited. And on the overall picture, wind, solar, hydro, all these are free, but they are not always usable. That's the challenge. How can smart grid help to deal with that challenging situation? Let's look at wind energy first. Okay, this is data from Northwestern United States. BPA stands for Bonneville Power Administration. I'll show you 4 pictures, 4 seasons. This is winter in the US, January 2013. Typically, in the winter time in the US, power utility has 2 peaks. Morning peak about 7, 8 in the morning. You'll get up, start breakfast, get ready to go to work. And then about 6, 7, and people come home and load goes up again. Typically winter time. It's not a big air conditioning load in winter time. So that's the demand, the blue line. The red line is the supply. This is real data from Bonneville Power. The scales are different. Left-hand side is the power demand, megawatt. Right-hand side is the wind output in megawatts. You see, the wind output is the highest. It's the average for the month of January 2013 at about 2 p.m. Demand is very low. They don't match. That's one challenge. Let's look at a different season, April 2013. Similar thing, again, dual peak. The wind output changes from season to season. Very obvious here. High at midnight and then slowly goes down to minimum about 7 p.m. or 6 p.m. when your load begins to pick up. Doesn't match. Let's look at summertime. Summer load, because of air conditioning in the US, is typically single wide peak. Again, the blue line. Summer wind is low in the western US. See the very low, about almost close to 0 at 5 p.m. when the load is very high. Again, not a good match. Finally, fall, autumn season. Again, you get 2 peaks, no air conditioning. Load is fairly good. Fairly well known. Supply is fairly good. Wind is matching pretty well with the demand picture. But then when the evening load happens, peaks, the wind is low. That's your challenge. This is wind in northwestern US. Let's look at other example, short-term variation. This is data from a wind farm in Texas, 150 megawatt wind farm. Suddenly at about 6 a.m., it was producing 140 or so, goes down to maybe 80. So 44 megawatt drop in 1 minute. That's a huge headache for Dean Sharafi's people to manage the load. Huge headache, and that's the reality. Even bigger headache. Look at this one. Same wind farm, different day. 5:30 a.m. The drop. It was 140. Drops to about 20 megawatts for an hour or so. Then picks up again and stays flat. So this is the challenge. Okay, more challenges. This is again Texas, 2008. Data from the state as a whole. 4,541 megawatt wind capacity. So in the morning, January 1st, producing about 2,200 megawatts, 50%, not bad. Keeps on dropping. By 11 a.m., it gone to 100 megawatts, from 2,200 to 100. Stays pretty low, slowly picks up. By 8 o'clock, it's better, maybe 700. Next day, similar things, slow in the morning, picks up. By the end of the day, it's pretty close to 2000 megawatts. So see what happened over a 48-hour period. Wind was high, drops, stayed flat, and it picks up. This is longer term, but it is a problem. If I go to the next 2 days for the same wind farm, it's pretty full. Almost 3000 megawatt, 2500 megawatt all day. Then the question is, if you are telling me this is your challenge, it's fine. I have a lot of money. I'll buy batteries, fill up those gaps. You can do that. But you come to this picture, you don't need the battery anymore. You've invested money in buying those batteries not being used. Any businessman tell you, unless I get return from a battery, I can invest. So the battery is not a good solution for this longer term variation. You can build gas turbines. Again, they would not be used every day. So this is a challenge we can deal with as we go forward. Okay, so now solar. This is my building at Virginia Tech near Washington, D.C. This is the rooftop solar I put in there to see how the solar output match with my building load. That's the objective. This is a summer day, fine. We have also winter days. Same field. One morning I go in there, sunny outside, you can see the sun, but no power. So I didn't know the roof is covered up. We don't go to the roof and clean and broom the snow. We don't do that. So now you have full sun, but no output. Another challenge. Okay, now if you look at longer term data from the same system, 7 days solar PV output, I picked a good week and pretty good. My capacity about 6 kilowatt. I'm getting about 5200, 5400 kilowatt, 5400 watt, 5.4 kilowatt most of the days. Pretty good. That's 1 week. A different week looks like this. This is your system. So you get hardly 2 kilowatt, maybe 3 kilowatt. One day I got about 5 kilowatt, then again 2 kilowatt or less. That's my experience. That's the weekly data. If I look at a day, like here, it is pretty sunny most of the day, a lot of fluctuations up and down, up and down. That's the challenge. I'll tell you how I can use smart grid to address this fluctuating supply. That's a good day, but clouds move in and out. Bad day look like this. You have no control over sun. Sun will do what he wants to do, or sun does what it does, but cloud you have no control over. This is your ground reality. These are the challenges. Okay, now, this is the solutions I talked about already: battery storage, pumped hydro for longer term, then something new called compressed air storage. You can use off-peak power from nuclear, from wind, doesn't matter, to compress air and put that compressed air in a salt cavern. Salt caverns are usually sealed. And hold it there, and then when you need compressed air to run a gas turbine in the afternoon on a summer day, let the compressed air come out of the cavern and go to the gas turbine. As you know, most of you, for a gas turbine, you have to compress the air before you fire it. Now you compress using a motor. But here, the source of that compressed air is the air they stored using off-peak power. Those are all possibilities. Some are shorter term, some are longer term. Like this compressed air picture has a daily cycle. You compress at night, use in the afternoon. The battery is a cycle every minute. It could be second by second, up to you. Pumped hydro also daily cycle, sometimes weekly cycle. You pump and store over the weekend, use during the weekdays, and also pump at night. So those are different variations, possibilities. Fine. Then the other question is, if I have this kind of supply issue, I could manage this by changing my load in real time, I'll be in a better shape. That is what we call demand response. The top part of the screen, demand response, is a customer action to control load to meet a certain target. Here, the customer chooses what load to control and for how long. Example, I have a house here. Summer afternoon, power company needs some savings because they cannot handle all the demand. They tell me, okay, Dr. Rahman, can you drop your load by 5 kilowatts? What I'll do, I can have a home energy management system monitoring my air conditioner, clothes dryer, water heater, electric vehicle charging, and electric oven. 5 things are happening at the same time, all of them 220 volt in my case. I can make a system so that they can scan everything and make a recommendation. What needs to be turned off for how long to give the power company 5 kilowatts for 2 hours, they're asking. It's possible now in demand response, but not widely used because most people don't have this home management system to scan and do this work. The other thing that has been happening for many years in the US and Australia as well, demand side management. Power company, with your permission, can turn off your air conditioner when the demand is high. That means on a hot summer day, you are home, your AC turned off because they want to save energy. It gets some money from them, but that's inconvenience. I said, that is not something people want to live with, but give me some technology which will scan my loads and decide automatically what can be turned on, turned off for how long, so that I can provide you the supply savings you're asking for. That's the difference. Okay, now, this is the summary of the problem. Historically, we have done what we call demand-driven supply. Power companies make long-term forecasts, 20-year forecasts. Based on that forecast data, they design and build power stations. You want to stay ahead of the load always. You build a 1,000 megawatt power station, take some time to catch up and keep on building. That's called demand-driven supply. That's the standard practice. Now, when supply is fluctuating, that's a different thing. As supply fluctuates, demand needs to adjust to meet the fluctuating supply. If I could adjust my building load by changing air conditioning temperature setting, light dimming, I could take into account these short-term solar variations and use some storage. As I said before, I can use a lot of storage, but that's expensive. If I'm smart, I'll play with storage as one element of the solution, not only element of the solution. Demand is my bigger, cheaper way to deal with it. I call that the smart grid ecosystem. That's my smart grid ecosystem. Let's start with the smart building, the yellow circle at the bottom. Smart building has building automation system, smart devices, grid integration, all of that. Then multiple smart buildings like Curtin University, for example, a smart campus. The buildings on the campus can be made smart by deploying these technologies. Then you have a smart city, Perth, then Western Australia. This is your Dean's company, kind of smart grid. So at the bottom, the core is smart building. I say you cannot have a smart city without smart buildings. People don't realize that. People have smart city conferences, smart city seminars. People come in from mayor's office, from the government. I said, fine. But how are you going to deploy this? This is the ecosystem that I am putting together to make it happen. Okay, moving on then. So what makes a building smart? A building has air conditioning, heating, lighting, water supply, sensors, security camera, fire emergency. All of that is the fact of life in a new modern building. What I'm saying, all of those applications must be brought in to one control panel for the building engineer and see what's going on. They can decide to dim the light in a conference room not being used, for example, save electricity. They can raise the temperature for AC in a classroom, nobody's there. Right now we don't do that. Everything is the same, all the same temperature, whole building, same lighting. That's the smartness in a building we need to work on. Okay, that's one building. If you have a large number of buildings, like a campus we talked about, you can then play between buildings. For example, a building has mainly classrooms, 4 o'clock in the afternoon, classes are not happening, but still AC running, lights running. Next building could be a conference center. where people are coming in to hold an afternoon conference. They need the power and the air conditioning. If I could save some electricity from that classroom building and supply to the neighboring building with conferences, I don't have to buy more from the power company. We do this at Virginia Tech. We have on our campus 121 buildings, and we're trying to manage it so that we don't buy extra power during peak hours, which is very expensive. But for that to happen, I don't want too much storage, minimal, but I have to invest in monitoring and control. Monitoring means the classroom building must be monitored, occupancy, temperature, and control the air conditioning load and supply to the neighboring building. That's the concept of cumulative building management or smart campus. So how do I address the intermittency of the renewable using smart grid? First of all, smart versus not so smart load control, the first bullet. What is not so smart load control? I said already, my power company gives me some money every year to turn my AC off when they want to. They don't care if I'm home or hot. So I don't want that. I would rather tell them, don't turn the thing off. You can set the temperature higher. It's now maybe 20, make it 22. I can live with it, but don't turn it off. That's the smart control. By scheduling the temperature setting changes, they can cycle a bunch of homes at a time to get the saving they want, but not giving me uncomfortable situation inside my house. So this is the first stop. Second stop is, yes, I need storage, but you should not do a brute force storage calculation. I have 10 kilowatt demand by 10 kilowatt battery. No, look at the opportunities for demand control as well. Also, you can look at the PV output. You can have smart inverters for the rooftop solar and control the output to make sure you're not creating overvoltage. It's happening in California today, San Diego. Mid-morning, 10 o'clock in the morning, people are not home, sunny outside, rooftop solar producing on capacity. They're sending power back to the distribution network, voltage goes up. So if you have a smart inverter, you can take care of that situation. Okay, now that's done. Now reality. COVID-19 and IEEE. I have been asked this question many times, that what am I doing? We realize COVID is a fast-moving, uncertain, and complex situation. We all know this. We also know that we will get out of this. So when we recover from this, we have new normal. New normal is many will be working from home. This will be real life. How you deal with this? IEEE can play a role by offering cooperation, collaboration, community spirit. For example, as I said before, microgrid is a situation, my house needs more power, my neighbor is not home. Can that be used, the excess power from my neighbor, turn his or her AC down, meaning raise the temperature up and save it? That's called community spirit. IEEE has a lot of content to deal with this, but we don't talk about it. This is my challenge as a candidate to let's talk about this so that we can be contributing regardless of in Australia or in the US or in China, India, doesn't matter to do this. So for that to happen, I want to make IEEE more broad so that Australians can come in as well as Chinese and Indians and Europeans and South Americans feel we are part of a same community. So this is my last slide. I have not spent too much time here. The reason I put it in, so you have my email address. Any questions that I can address today, please email me your questions so that we can have a dialogue. And then I have a website, www.srahman, my name.org. There's a lot of information if you're interested in this. So I'm also on Facebook, LinkedIn, Twitter, and YouTube. It's up to you what you want to do this. I'll stop here, Dean, and then take questions.
Thank you very much, Saifur. Very informative and very relevant to Australia, what you said. Here in Australia, we said if you own your home and you don't have a rooftop solar on your home, then you need to see a psychologist. Because almost 1 in every 3 homes have solar rooftop. Okay, we have some time for questions. On the left, on the right-hand side, there is a chat box. So if anybody wants to pose a question, please, and make it visible to us.
You know, as somebody thinks about the question, I'll give an example. You talk about Australia. I was in Hawaii last year. They have similarly, Honolulu especially, a lot of incentives for rooftop solar, and many homes have put solar, and in over there you get a lot of money back from the government. Anyway, the point is, power company says, well, and Dean's company will appreciate this. We, power company, have you connected, give you power when you need it, but you're not buying in the afternoon or in the evening, in the morning time because you have a lot of solar. So I, power company, my cost has gone up to serve you. I'll charge you more money, called connection cost. That has gone up significantly. So to avoid the connection cost, you have to go disconnect from the power company. So disconnect. You can disconnect only if you got battery, of course. So Hawaii, on many homes have done that. They're disconnected. They bought the Tesla wall battery, rooftop solar, and they're happy. So this is the next generation. That now you are your own microgrid. You're managing a load. For example, your battery is kind of low at, I don't know, 6 p.m. So don't use the AC that much. Don't dry your clothes at 6 o'clock. You can, but don't do it. That's called microgrid management. That's the awareness, smartness, as well as the homeowner's willingness to deal with the system. This is happening today, that disconnect from the grid. Not good for anymore, but that's reality.
Yes. So, Saifur, I can't see people's questions. Maybe they are posing questions here, but I can't see. But I have my own question. So, know that I can talk to you, and hopefully everybody can hear us. What do you see the role of Internet of Things and smart data in facilitating what you just said? You know, the absorbing intermittency of generation that increasingly are not fixed. They're intermittent, and the fuel is nature, effectively. How do you see the role?
That's a good question. IoT, Internet of Things, is the benchmark, is the linchpin connecting this. Why? As you saw in my data, you must be able to monitor in real time what's happening and react in real time. So I have shown, and the picture is not there, smart thermostat, smart lighting switch, smart plug, smart air conditioning control, smart ventilation fans. Those are IoT devices. So they have to monitor real time. Without those devices, none of the stuff I said would not work. So you're right, this is linchpin. They are the ones making it happen. But the question is, you can monitor fine. You know what's happening. If you cannot control, you don't solve the problem. So I have another set of slides, I didn't show it here, on that very topic. How do you control? So what I'm saying, if I see my load is growing, I would want to keep the demand fixed because of my rooftop solar has a limited capacity. I would control my air conditioner automatically. In my examples I've done, I've seen if you raise the temperature by 2 degrees centigrade, you save over 15% energy savings over a day. So those numbers are in my algorithm built in. IoT is giving me the sensor data, comes to my algorithm, it takes some actions, and they raise this temperature by 2 degrees for this AC, dim this light, turn the bathroom fan off. All that can happen automatically. That's what we do.
Excuse me, there are a couple of questions that have come through. I'll ask them and you in turn can answer. Is storing excess RE in the form of hydrogen a good solution to keep the grid stability?
Yes, if you ignore the money part of it. In theory, yes. I have done the research myself. I worked on hydrogen economy. I did a conference in DC on hydrogen economy, for example. Very expensive. Hydrogen is made from water, either by electrolysis or heat application with the steam application. Pretty expensive. So, and in theory, yes, but today it is cheaper to put that in a battery than make hydrogen.
Okay.
Next question.
How do you deal with distributed network constraints?
Okay, distributed network constraints, if I'm understanding the question properly, it has capacity constraints, transformer constraints, and it has timing issues. For example, let's focus on a distribution network in your neighborhood. If you have, like Dean just said, many homes, 1 in 3, rooftop solar. In a mid-morning, you're not home, you're sunny outside, making a lot of electricity from the solar panels, you're trying to send it back to the grid. Now you have reverse supply. The switching circuit was designed to see power coming in, line grounded, and then disconnect. Now power is going backwards. Those have to be really thought about and revamped. The switches must work both ways now, not single way. So those are the elements of the smart grid we have to be talking about. So Dean knows this very well. To solve that problem, you cannot solve all of Western Australia in one go. You have to solve it part by part. So what I'll see will happen in the microgrid examples where this is happening. And then once you get enough experience by the engineers, you can begin to spread out and go to the whole system. Example, I'm working with a company in Chicago, in the US, Chicago. They have a downtown microgrid called Bronzeville microgrid. It's about a 15 to 20 square mile area space. They have office buildings, hospital, school, rooftop solar, battery storage, all of that. Try to gain experience how to deal with this, the local supply from rooftop solar. Then engineers feel more comfortable to expand out. This is going to happen, take time, but start small and then grow. Next question.
What does a power system look like in 50 years' time?
It will look like, as I said in my example before, I'll go back to that picture. Give me a second. Can you see this picture? Intelligent, interconnected microgrids. Dean, can you see? He's muted. Okay, he sees this. This is the 2050, 2045 power system in Perth. This is how it looks like. Every home has rooftop solar. Many have batteries. Everybody has electric vehicle. Everybody has control, monitoring, IoT applications, and this is life. This is where people like Tirthankar Banerjee can make money by giving advice to owners like you and me.
Okay. There's a question that refers to your reference from Curtin that you have mentioned about the voltage rise in rooftop PV. What are the solutions you see feasible, as this is a problem for Australia as well?
Right. Very good question. I have done this in my lab. I wish I could show it to you here. I have put a smart inverter which can be remotely controlled to change its power factor. As you know, power has two P and Q, real reactive power, and that controls the power P and Q for voltage control. In the US, problem, I'm sure, happening in Curtin as well, where you are in Perth. If you do not do any control, the inverter, all it does, makes AC out of DC. As the supply side power begins to grow, the power flows back to the grid and voltage begins to rise, obviously. Load is not there. In the US, voltage is allowed to fluctuate plus minus 5%. 120 volt, my single phase line, can be 126 or 114. Beyond that, power company can be penalized for this. So what happens now, when this is practice today in the US, in California especially, when the power company sees my inverter is putting excess power to the distribution network, voltage is rising, they turn the inverter off, just off. But that's not good for me. I was hoping to make some money by selling energy during the morning hours because I have to pay back for my rooftop solar. It's off. The better solution is let the power company have, this is a fact, California, Illinois, now requiring any new PV must have smart inverter, which can be remotely controlled. So what the power company does, I do in my lab, I will change the cosine theta power factor. The voltage drops and stays dropped. When the voltage profile is improved, I let that control go back up, the more energy comes through. The net effect is before the power company turned the inverter off, zero output from me to the network, zero. Now they turn it down or off. The voltage is within limit. I'm selling 80%, not 100%. It's better than zero. That's the solution that I would like to see. But for that to happen, the homes must have a smart inverter, and Tirthankar knows this. Number one. Number two, they must be controllable from some substation to make it work. Next question, if any.
When do you think that we will have a full smart city according to the view that you said?
I hope Perth will be one of those. People like Dean and the rest of them make it work. We do a conference, IEEE, every year on smart, IEEE Smart City Conference, ISC squared. We did one in Casablanca last year. So we bring the mayors. He pointed the following. We engineers can think of many different things, but it doesn't work unless people on the ground accept it and then make it work. So we invited the mayor of Casablanca to listen to us and give us his ideas. So I think for smart city example, the biggest bottleneck, not the technology, not even me, we know what to do, is the application field. So we have to be open and able to convince the administration it is beneficial. First question they ask me, money. Then you get stopped. It's too expensive. So then I give my example of black phone and smartphone. $15 and $1,500. 1,000 times to pay for paper because you give more stuff. Our job is to convince the city administration, if you want smart city, you get these benefits. That's the challenge. Unless I can do that very convincingly, things would not move as fast as we would like. The answer is education.
Yeah, thank you, Saifur. I'm conscious of time. I know there's only 2 minutes to the end of this, and people may have commitments. Just I want to make 2 points. Firstly, I wanted to thank Saifur for this excellent presentation. But my other point was that Saifur is putting up for the IEEE president. Please encourage, firstly, vote for Saifur for IEEE president. Secondly, encourage all of the IEEE members that you know to vote for him. I have worked with Saifur in the last 3-4 years, and I know how dedicated he is to the cause of IEEE and Power and Energy Society. But this is a new role, and I think somebody at his capacity will be great for IEEE, the same as he did for PES. That's the second thing. And also, I wanted to thank Michelle because she was on leave and away from Perth, in a city north of Perth, actually very far from here. But she made this presentation possible, but bringing it all together. So, and thanks to everyone who attended. I think I saw about more than 110 people attending tonight. So thank you, everyone, and I hope you have a good night. And everybody is at night here. So thanks for attending and thanks for listening. And for questions, Saifur put together his contact details. If we couldn't answer all of your questions, please get in touch with Saifur. And thank you, Saifur.
Thank you very much, everybody. Take care. Enjoyed it. Good questions. Thank you. Good luck to you. Bye-bye.
Yeah.